Hey, if you think about how like a wood table leg or a wood chair leg is made, it's spun around and they use a lathe to kind of, cut the grooves into it. And so if we could slice it up, we would get a bunch of circles. So with the previous method, right, when we were talking about the slicing method, sometimes we got square slices or rectangle slices. Sometimes we got circle slices. But if the solid is created by spinning something around and around and around, in this case revolving around the x-axis, it will always be a circle when we look at the cross section. And since these circles that we cut are always going to have a tiny, tiny thickness, we call them discs. All right, so we have to start out with a region. I stole this off the internet. And we've got to spin it around the x-axis, or revolved would be the proper terminology, I guess. And so there it is, at kind of a skewed view as it starts to spin around. And then if we get it spun all the way around, hey, it's a three-dimensional object, so it has a volume because it's a three-dimensional solid. All right, now since I don't want to just steal images off the internet, I want to just make up some equations. Right, because I decided to make up this equation. I'm like, okay, I gotta try to graph this thing on my own. So I was like, okay, thank goodness for Desmos, so I can make a nice, easy to read graph. Right, there's a sine curve. I'm sorry, the cosine curve. It's been lifted up 2 units. I'm gonna go from 0 to 2 pi. And of course, I want to spin this. Now, my artistic ability is obviously limited compared to cutting and pasting off the internet. So you'll have to pretend that's a three-dimensional representation. And then of course, if I can cut this up into infinitely thin slices, right? If they had no thickness, they'd be circles, right? And the area of a circle is going to be pi r squared. But of course, they actually have a thickness, right? They're very, 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 very thin, but they do have a thickness of dx. And so if we multiply by the thickness, it becomes volume. So pi r squared gets me the area of a circle. And then because there's a thickness, we actually are ending up volume. So we just need to add all of these up. So I'm going to start on the left-hand side at 0. I go all the way to the right-hand side, which is 2 pi. Now again, because I'm trying to show a 3D representation, it looks like the shape starts before 0, but you got to kind of imagine we're kind of looking at it like a slight angle, right? I try to make it look three-dimensional there. And so, at the other end, you're kind of like looking at like either the bottom or the top of it, depending on what your perspective is. Got to do a little bit of FOIL action, right? First, outer, inner, last. That's where that cosine squared x plus 4 cosine x plus 4 comes from. Got a problem child here, right? Cosine squared x, if you remember, we got to use a table of integrals for that. So sure enough, if I use the table of integrals, I get x over 2 plus 1/2 sine x cosine x. Integrating cosine becomes sine. 4, when I integrate it, becomes 4x. Again, those silly coefficients just sit there and look cute. Got to plug in 2 pi for every single x. Got to plug in 0 for every single x. 2 pi over 2, let's call that pi. Plus 1/2, better keep it. Sine of 2 pi, let's look at the unit circle. Oh my goodness, that's 0. Cosine of 2 pi, look at the unit circle. Oh, that's 1. Plus 4, better keep it. Sine of 2 pi is 0. 4 times 2, I bet that's 8. Now this is really sweet because as we go through the second integral, although not everything becomes 0, every term though, when I end up multiplying it, each one of those terms will turn out to be 0. So that really speeds life up, right? So a whole lot of stuff canceled. Pi plus 8 pi gets me a 9 pi. 9 pi times pi gives me 9 pi squared. And of course, that is in cubic units. Dun, 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 dun. Okay, so before you panic and think, oh no, it's all going to be ugly trigonometry stuff with tables, nah. Let's make up one where we don't have to worry about some of that crazy unit circle stuff or an integral table. And again, I'm like, what on earth does the graph look like? Well, if the teacher doesn't provide it with you, you could be just like the teacher and you can go on to Desmos and say, hey, Desmos, could you please graph this for me? And now, again, instead of trying to steal it from the internet, here is my attempt to look like it has been spun around the x-axis. Right, you gotta pretend it's three-dimensional. So kind of like I don't know, like a three-dimensional teardrop or a water drop or something. And of course, the radius is just going to be the distance from the x-axis to that curve, which is just going to be negative x plus root 3x. And so the area for any one of these slices, if we look at the circle that happens when we slice it, again, you got to imagine this is three-dimensional, but because of the viewpoint, that doesn't really look like a circle, but you got to remember that, right, it's supposed to be a circle, right, but I'm trying to make it look three-dimensional cross-section. Pi r squared. And of course, when we multiply by the thickness of dx, and we can put it in the integral. Now this time I'm going to show the FOIL. I did the FOIL last time, but I didn't show it step by step because I figured you can figure out cosine times cosine makes cosine squared. You know, 2 times 2 makes 4. This is a little bit trickier though, so I'm going to do the first, outer, inner, last. So negative x times negative x, that's first. Outer, negative x times root 3x. Inner, root 3x times negative x. Last, root 3x times root 3x. Now, to simplify this, because I've got to integrate at some point, something, whoa, how am I going to do this? I'm going to pretend all those x's have exponents, right? Plain old x is x to the first. Square root of x is x to the 1/2 power. Square root of 3 I'm obviously leaving alone. And then at the caboose, square root and squared outdo each other. So, boom, 3x at the end. And so that allows me to figure out, oh, okay, I've got an x to the 3/2 power, right? That came from O, but then also from I, there's an x to the 3/2 power. So let's kind of write this in correct order. I'm going to have the negative sign. I've got 2 identical terms, so there's a 2. Then I'll put the root 3, and then finally I'll put the variable x to the 3/2. And that is what I need to integrate. And of course, integration here is straightforward. Oh, I should mention, I don't know if I mentioned in the previous example, notice because pi is a constant, I put that in front of the integral symbol, right, on my pi r squared. I said, hey, pi is just going to sit there and look cute to the very end, so put it out in front so I don't have to rewrite it with all these different terms going on. Okay, so let's do some integration. X squared, of course, becomes x cubed over 3. On that middle term, I have to add 1 to the exponent. So 3/2 plus 1 becomes 5/2. But then I have to divide by 5/2. On that last term, x becomes x squared, but I got to divide by 2. The one that's crazy is that middle term. Remember, dividing by 5/2 is really multiplying by 2/5. And I can tidy that up a little bit more now. 2 times 2 makes 4. Okay, you got to plug in 3 every place. Got to plug in 0 every place. Woo, look at that. Now, the good news is when I plug in 0, everything in that second set of parentheses is just going to become 0. right? So yeah, the integration is kind of messy, but at least when we plug things in, I'm not too concerned about what's going on in the back half. Notice here I rewrote that square root of 3 as 3 to the 1/2 power, because that enables me to figure out that I've got 3 to the 3rd there, right? 1/2 plus 5 halves is 6 halves, also known as 3. So I'm like, well, what do I do now? Common denominator is going to be 10. So 9 becomes 90 over 10. 108 becomes 216. Actually, it was 108 over 5, so it becomes 216 over 10. 27 over 2 becomes 135 over 10. And so this answer is going to be kind of close to, what, 9/10 when we add those up, so that's not too far from 1. But then, of course, we're going to multiply by pi, so the final answer is pretty close to 3. You know, pi times 9/10. So there is the answer, 9 over 10 pi cubic units. I think on the assignment that I'm giving you that you'll find the integration is probably not quite so messy. And I think you'll find that I try to give you one on the worksheet where when you do the FOIL, you're not going to be playing with some messy trig, and I don't think you're playing with a messy square root either. I gave you kind of something a little bit more straightforward for your question on the worksheet. And so there is Suzalo Library on the University of Washington campus. And it's time for you to probably get to work.